What I have built is a testing facility for a space glove. That means this box replicates what it's like to wear a glove in space. But instead of pressurizing the glove, because I don't have a full pressure suit, I am negatively pressurizing the glove's atmosphere, i.e. this box will be a vacuum. So what this is a glove box that recreates the exact pressure differential from outside to inside for an astronaut. And it's also an arcade game, sort of. Let me turn it on and show you the features. That's the light, and that's the vacuum. Now, I pull it to, yeah, see, it's waking up. I pull it to 1 psi, 2 psi, 3 psi, 3.5 psi. All right, so once it's filled to the correct pounds per square inch of pressure, I'm astonished by how difficult it is to actually move around. The idea, like from the movie Gravity, that you could like reach out and grab something with one of these gloves? No way. Not gonna happen.
It was the biggest test so far of man's ability to use his hands and his brain together in space.
This is from the helmet-mounted camera, just how many wires are in there. I don't even know how many there were, but there's a whole bunch of wires.
This is the part I think I mentioned to you folks. If there was anything I really didn't think that we might be able to do, it was to change out all these little electrical connectors, and these guys made it look like a piece of cake, just like they'd been doing it all their lives.
There's 11 connectors, and each one of them had up to like 78 wires in it. But it turned out to be, after all the training we did earlier, wasn't very difficult.
I'm astonished by how difficult it is to actually move around. The idea, like from the movie Gravity, that you could like reach out and grab something with one of these gloves? No way. Not gonna happen.
There's 11 connectors, and each one of them had up to like 78 wires in it. But it turned out to be, after all the training we did earlier, wasn't very difficult.
Not gonna happen.
Wasn't very difficult.
Not gonna happen.
Wasn't very difficult.
I'm astonished by how difficult it is to actually move around.
Wasn't very difficult.
Not gonna happen.
After all the training we did earlier, wasn't very difficult.
People will argue, okay, if you put an apple into a vacuum chamber, it doesn't lose all its weight and start floating around. So you're wrong and gravity is right, and therefore we live on a globe. The first thing I'll point out is that the apple is more dense than the air before it's sucked out, so the apple is certainly more dense than nothing in a vacuum chamber after the air's been sucked out. In any case, it's conventional science's position that barometric pressure affects weight on a scale. So an apple will weigh a bit less at the top of Mount Everest. This observation is in line with barometric pressure as the cause of what goes up must come down, but how do we know for sure it's the cause? If you put an apple into a vacuum chamber and it doesn't lose most of its weight, it would still drop to the ground, of course, but the theory about barometric pressure rendering our mass with weight on a scale, if that were 100% true, then you would expect the apple to weigh much, much less in a vacuum chamber. Now, I've personally never done this experiment, but I believe the apple will only weigh slightly less, depending on the type of scale you use even, but this certainly hurts the hypothesis that barometric pressure renders most of our mass with weight on a scale, or that barometric pressure is responsible for most of our mass's weight. There are a couple of explanations for this that do not involve the conventional theory of gravity, and I believe it's possible that the matrix of reality is able to permeate superficial barriers, such as the outer wall of a vacuum chamber. And just because you can remove the air from such a chamber doesn't mean you can remove the matrix of reality from the chamber. So if we consider it may be possible that the non-physical matrix of reality transcends or permeates physical barriers, so the barometric pressure surrounding the vacuum chamber is still affecting the weight of the apple inside, even though there isn't any direct physical contact or relationship between the atmosphere outside the chamber versus inside the chamber. Inside, it would be void of atmosphere, with the lonely apple inside a bit lighter than it was before, depending on the type of scale you use. Now, I don't tend to subscribe to this theory, but if the observation is true, then there must be a reason why the apple in a vacuum chamber doesn't lose most of its weight that would be, of course, added to it by the column of air pushing down upon it from the edge of space down to the ground, which would be most of its weight in the conventional model. Again, gravity is only the tendency needed for down to be down, and an object on the ground is supposedly getting most of its weight from barometric pressure, constantly pressing it down towards the ground. People have argued that if you place an apple into a vacuum chamber and suck out all the air, the apple will weigh about the same and will not start floating around in the vacuum chamber, therefore the Earth is a spinning globe. The argument is intended to show that gravity is causing the apple to fall and that barometric pressure has nothing to do with weight on a scale or objects falling to the ground. One thing's for sure, since the apple is obviously of a higher density than the surrounding atmosphere before the vacuum is activated and all the air sucked out, then the apple would certainly be of a higher density than the atmosphere within the vacuum chamber after all the air sucked out, and of course would find its way to the bottom since it is more dense than nothing. The notion that the apple would somehow become weightless if confined in a vacuum chamber only makes sense if you ignore the primary principle involved with the physical laws of density and buoyancy. While the surrounding atmosphere near the ground is comprised of matter which is higher in density than the air at the higher elevations, if you remove all the air from a vacuum chamber, the apple will not float around and will of course fall to the ground because the apple is obviously higher density than the nothing which fills the vacuum chamber. This phenomenon would be affected by the density of the matter comprising the apple being more dense than the air. Then the apple is certainly a higher density than nothing in a vacuum, so it will of course naturally find its way down to the ground without the air pressure increasing the weight of the mass. On the other hand, I can imagine a vacuum chamber a few feet in diameter, but say is 500 miles tall. In that case, I can imagine the apple weighing considerably less, however, it would still naturally fall towards the ground since it's of a higher density composition than the surrounding medium, and is of course less dense than the floor or the ground, and would therefore find its place of rest naturally balanced on the ground. This brings up some interesting questions, of course. If barometric pressure does indeed increase an object's weight on a scale, you would think that if you put an apple into a vacuum chamber and suck out all the air, then the apple should weigh considerably less, since there's no column of air pushing down upon the object. This indicates to me that we're missing something in terms of a component involving barometric pressure. Here's what I mean. If an apple weighs, say, a pound at the bottom of Mount Everest, but only weighs 3/4 of a pound at the top of Mount Everest, we can hypothesize that the barometric pressure at the higher elevation is the cause of this. If you were to carry the apple to the very edge of space, say 350 miles into the air at the edge of the lower magnetosphere, the same apple will weigh a fraction of that. So there's a direct relationship between mass, density, barometric pressure, along with temperature, surface area. There's all sorts of factors that goes into this thing we call weight. Another interesting point to consider about atmosphere and barometric pressure is the resistance involved. A falling object will experience terminal velocity based on the density of the air and the surface area of the falling object. So a penny and a feather will fall at totally different speeds under normal circumstances here in reality. If you place the two in a vacuum chamber, however, they will fall at the same speed. This is because objects with a solid mass are attracted to the ground with similar force. However, the resistance of the atmosphere plays a role in the terminal velocity or maximum falling speed of an object. Another important observation to make here is that, and thanks to Fran Anderson for pointing this out, if you actually watch the feathers and the bowling ball in the Brian Cox experiment in NASA's largest vacuum chamber, apparently the feathers actually fall faster than the higher density object, so that raises some important questions.
Well, of course I had to check out the other footage. It wouldn't be fair to just examine the most popular and publicized video. The reason I said that maybe our actor crew was watching the feathers beat the ball to the ground was because that's exactly what I saw over and over again when I slowed down the other videos of this type of experiment. The other videos varied a lot in their presentation style, and some used tubes while others used a chamber. But in all the videos, lighter objects stay ahead of the heavier ones. This particular video was tricky to slow down because it all happens in the blink of an eye, but the feather clearly beats the ball.
The best way I can theorize this, if we're going to stick with the theory that similar densities are attracted to the ground, then let's think about it this way. Any physical matter is going to be vibrating at a certain state or phasing with a certain harmonic resonance that is conducive or similar to that of the ground, and so there's just an attraction between these similar harmonic resonance or similar frequencies, if you want to think of it that way. And if the bowling ball and the feather in the vacuum chamber or outside of the vacuum chamber fall through air, then you have the buoyant force, which is going to affect the feather more obviously, and the heavier, denser ball is going to hit the ground first, obviously in regular atmosphere. But when you remove the atmosphere, since there is no buoyant force, then there's essentially, the heavier, denser object doesn't have that leg up on the feather in terms of the race to the ground, and so you have essentially less work. Since the feather is less matter, it's lighter, it's less dense, it's less work for the ground to pull it towards it, or for whatever this force is, call it gravity, call it the natural balance, but it's more work to pull the heavier, denser ball to the ground than it is to pull the lighter, less dense feather to the ground. And so I could see that being a bit easier for nature to pull the feather to the ground, and there isn't the hindrance of the buoyant force, which would normally, be very compelling on the feather and wouldn't hardly affect the ball whatsoever. This clearly shows that the atmosphere contains some matter and has resistance. If you compare that to the void of space, which is supposedly a vacuum, then we must somehow explain how the matter-rich atmosphere is pressed inward by the void of space. How is this possible? If the mass of the Earth is displacing the void of space-time, in other words, it's displacing nothing, then how can nothing exert any force on our atmosphere which contains pressure and matter? So, with all that in mind, you would expect to see an apple placed into a vacuum chamber to lose most of its weight on a scale due to the barometric pressure column above being severed. However, it only loses some of its weight, and that's only depending on what type of scale you use. This fact is often used to prove the conventional explanation of gravity. However, I'm not so convinced. For one, the matrix of reality that houses the apple and the vacuum chamber is possibly transcending the barrier of the vacuum chamber without physically penetrating the outer casing of it. In other words, some force continues to render the apple with essentially the same weight on a scale, even without the physical atmosphere involved whatsoever. On the other hand, we should also consider Archimedes' principle. This is a theory of fluid dynamics, and yes, gases are also included as fluids on a larger scale. But Archimedes' principle indicates that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. Archimedes' principle is a law of physics fundamental to fluid mechanics. This gets a little confusing because on the one hand you have barometric pressure increasing the downward pressure on our mass towards the Earth. This is proven by traveling to the top of Mount Everest and you weigh slightly less. On the other hand, you have Archimedes' principle, which essentially states that the air we displace actually pushes us upward, like a buoyant force. So in a vacuum chamber, depending on the type of scale you use, the weight of an object would actually increase with the vacuum if you're using a modern electronic scale based on load cells. The upward force due to Archimedes' principle will decrease because the density of the surrounding air decreases. But if you were to use an antique scale, like a triple beam, the apparent weight would depend on the density of the object, as weight is only a symptom of an object's density and atmospheric pressure.